Hey guys, today we're going to be talking about finding the area of regular polygons. And if you want to follow along with some of the notes, these are on page 807 and 808. A lot of the vocabulary words are on those pages, so you can write them down as we go. So we're going to first kind of define a few terms with regular polygons. So now you have a regular polygon. We're going to use a hexagon here. There's actually two circles that are important with them. One circle with a regular polygon, there's the circle that you can draw that will be circumscribed about said polygon. So if I draw in a circle here, it would look kind of like this. This is not the best circle, but it would look like this. You can draw that circle, and that circle is circumscribed about the hexagon. The hexagon is inscribed in this circle. The center of that circle, right here, we'll call it point G. We call that the center of the hexagon, the center of the regular polygon. So in this case, it's a hexagon. And what's special about this, if we look at this red circle here, since it's circumscribed, it intersects at each one of the vertices. So the radius of this circle is going to be the same distance to each vertex, and we call that the radius of the polygon as well. So all of these are going to have the same measurement, and down here as well. We call those the radii of this polygon. So like GA is a radius, GB, GC, they're all radius, and they create some nice isosceles triangles, which will be useful. If we were to continue all the way around, we're going to end up with, in this case, 6 triangles if we were to go all the way around. And let's just do it. We're going to have 6 triangles. So the number of sides you have, that's how many triangles are going to be formed by drawing those radii in. And notice, since this is a regular hexagon, all of your sides along the outside are also congruent. Each one of those triangles inside is going to be a congruent triangle. And what's useful about that is all these angles here, they're all going to be congruent angles from corresponding parts of the triangles. Those little blue angles that I marked off, we call those the central angles of the regular polygon. And since they're all congruent, they're going to have the same measure. So the measure of those angles, well, the complete angle is 360. So you divide by the number of sides. So in this case, we have 6 sides. So each one of those angles, in a hexagon would be 60 degrees. It's different in every regular polygon. So that's how we can look at the outermost circle that can be drawn. I'm going to try to redraw another hexagon here. We can compare a different circle that gives us some special properties in hexagons. So if we have the same hexagon just over here, there's another circle that unlocks some special properties. This is a circle that can be drawn inscribed within the polygon. So it would look like this. And it's not terrible. And we'll call it point G as well. So this point G over here on the inscribed circle and the circumscribed circle, it's the same point G. Those two circles, the red and the orange, they're actually concentric with one another. They have the same center. For the red circle, it's going to give us the radius of the polygon. For the orange circle, well, the radius of the orange is going to be, there's like a point of tangency down here. It's going to be the distance from the center of the polygon to one of the sides of the polygon. And our special term for this is the apothem. I'm going to call it A for apothem, spelled like this. The apothem is the shortest distance from the center to the sides. And we're in a regular polygon, so it's going to be the same for each one. And it is perpendicular, that's what happens when you're the shortest distance. And this is going to be really useful when it comes to finding the area. Now, let's go ahead and try to redraw. And we'll see some other things that we know about regular polygons. So I'll just stick with my point G. So when you draw those radii in, you create an isosceles triangle. The apothem here, it's going to break that triangle if I take this triangle right here, this isosceles that we drew, this would be the radius, this would be a radius, this is the apothem of the, in this case, hexagon, and down here for these triangles, the whole length is the side, so each one of these is going to be half of a side measurement. This can all be really useful when trying to find different measurements. And like I said, in this over here, you're going to end up with, for a hexagon, 6 triangles, depending on how many sides you have. So since we have 6 sides, there's going to be 6 congruent triangles that we create there. And we're going to use all of this together to try to figure out how to find the area of different regular polygons. So let's go ahead. I'll do a pentagon this time. Try to make a general formula. Let's say we have a regular pentagon. And that's better. And we are trying to find the area of this shape. So let's say we take the center of the pentagon and let's focus on one triangle. Because like I said before, if we draw the rest of these triangles in, we're going to end up with, well, since there's 5 sides, we're going to end up with 5 triangles that are they're all congruent to one another. And if we can find the area of one of those triangles, then we can just multiply by 5. We have the area of all of them. So let's focus on this triangle here. And I'm going to kind of draw it a little bit bigger. So this little triangle, we'll draw on over here, this guy. So these 2 sides up here, they are both congruent. They are going to be the radius of our pentagon here. This side going, or this, really the altitude of this triangle going down in terms of the pentagon, that is the apothem. And down here on the bottom, this whole length, this is the side length. So if we want to find the area of just this triangle, well, it's nice to know that these are the radius, but they're not going to help us find the area because we can just simply use 1/2 base times height. But 1/2 your base is the side length, your height is the apothem. So 1/2 base, not 1/2 equals, area equals 1/2 base times height. And that would give you the area of this triangle. If we were to draw them all in, like I said, there would be 5 of them. They would look like this. The number of sides you have is going to be the number of triangles. So if we're trying to find the area of this whole pentagon, it's going to be 1/2 base times height, which is our side times our apothem, times the number of sides that you have. In this case it's 5, but for other polygons it might be more or less than 5. So this will be your formula. You find the area of one triangle, multiply by the number of sides you have. And what we can really do with this, 1/2, we'll say the apothem. If you think about the length of one of the sides, down here, and you're multiplying it by how many sides you have, in terms of the polygon, that's just the perimeter of the polygon. Length of one of the sides times how many sides there are. Since it's a regular polygon, they're all going to be the same length. So this will be the formula you can use. You can kind of think of it in this way. If you can find the area of one of the triangles, you can multiply to find the area of the whole polygon. But if you know the perimeter and the apothem, then you can do this as well. Really, it's just knowing where the formula comes from because you can use it in different ways. So let's do a couple of examples on how we can use this formula to find the area of different polygons, regular polygons. So let's see. Our first one that we're going to look at, we're going to try to find the area of a regular, what do I have here, hexagon. A regular hexagon, and the only information we're given is the hexagon has a radius of 10. And we want to find the area of this hexagon. So we have a hexagon. Do my best drawing. And we know there's a radius of 10. Now I'm going to draw these in. So we need to use some special properties. I think we know they're all 10, so I'll just leave them. We need to use some other special properties. Some of the things we need to use here, well, it's going to be useful to use that apothem, but it's also going to be useful to figure out all of these angles. So this whole complete angle is 360. Since there's 6 of them, they're all going to be congruent. The central angles in regular polygons are going to be congruent, so you divide by 6. So each one of these angles is 60 degrees. Now that can be useful. If we were to draw the apothem, draw it in right here. We don't know what it is, I'll call it A. We know that this is the apothem, we know this length is 10. There's a few different ways you can do this. I'm going to kind of focus on just this little triangle right here with the 10 up here. This was a right angle, this is the apothem, that's what I'm taking out, this little triangle over here. And this angle up here, the whole angle is 60, but this apothem is going to create like 2 congruent triangles. So this is going to end up being 30 degrees in here. And this angle down here then has to be 60, which makes a nice 30, 60, 90 for us. Since this measurement is 10, this measurement down here is going to be 5. A special property on a side note in hexagons, the triangles that are made when you draw the radius, they're all going to be equilateral triangles. So your radius is actually going to be the same side as, or same length as your side. And since this is half of the side, it's going to be 5. So if I take that information, put it over here, I know this is 5 and this is 5. The whole side is 10. We still need to find the apothem, but through 30, 60, 90s, we should know that A is going to be equal to 5 radical 3. So that's your value of A. And I'll go ahead and use the formula. The area is going to be equal to, well, it's going to be 1/2 the apothem times the perimeter. Since we have 6 sides, the perimeter is 60, and our apothem is right here. So 60 times 1/2 is 30. 30 times 5√3, so the area is going to be 150 times the square root of 3. We don't have units, we'll say units squared. So that would be the area of a regular hexagon, given that the radius is 10 units. We'll do one more, and then you'll try some of these on your own. So this one we're going to go to a pentagon. So here we're going to have a pentagon, a regular pentagon, and it's going to have an apothem of 5, and our goal is to find the area. So let's draw our best pentagon. That's a decent regular pentagon. Not to scale though. So we know, here's our center of the pentagon, we know the apothem is 5. So this right here, this is 5. We don't know the measure of the radii. We don't know the measure of a side. But maybe we can use some other pieces of information to find out what we need. So, if you think about the central angles, each one of these whole angles, this whole collective angle down here, there's 5 of them. So, we're going to do 360 divided by 5, and that should get us 72. So each one of these angles is 72 degrees. If you look down here, I'll kind of zoom in on it. If it's 72 for the whole angle, each one of these is going to be 36, and this is going to be a length of 5. Our goal is going to be to find the length of the side, so then we can find the area. So we have 36, we do have 90 down here, and we'll just call this x. The whole side will be 2x. So for this, we have to go back to a little bit of trig here. We have a right triangle. We have, in relation to the 36, we have the adjacent side. We need the opposite side. So if we use some trig here, tangent of 36 is going to be equal to opposite over adjacent. So x over 5. So 5 times tan 36 is going to be equal to x. And if we do this, let's go ahead and calculate that out. Tan 36 times 5, we'll round to the nearest tenth. We're going to get x is 3.6, so that means 2x would be 7.2. and that's going to be your whole length. That is the side of the pentagon. Since there's 5 sides, the perimeter would be 7.2 times 5. So our perimeter, for this is going to be 36. And if we're trying to find the area, well, then we can say the area is equal to 1/2 the hypotenuse 5 times the perimeter is 36. So 1/2 of 36 is 18. So the area is 5 times 18. And when you do 5 times 18, you should get, hopefully, 90 units. And we're squared. So that would be the area of the pentagon. This is how you can kind of use the formula. You need to use those central angles. The hypotenuse is really important. If you know the radius, you're going to be creating right triangles here that you can find missing sides with. Sometimes you need a little bit of trig, but we know how to use trig, so that should not be a problem for us. Alright, so go ahead and try some of these on your own, and have a nice day.